So, a couple more things about working with exponentials here. First, we want to look at how we can solve some basic exponential equations using the like basis property. So, here's the big idea. If we have two equivalent expressions and they have the same base, then they must have the same exponents. And this is this like basis property. Well, what does that mean? Well, that means this. Here I have 2 to the 2x plus 3 and 2 to the 15th. Well, 2 to some power equals 2 to some power. Those two powers must be the same. Because whatever 2 is raised to, if both sides are equal, then these two highlighted things have to be equal. In other words, 2x plus 3 equals 15. Now we don't have any exponent. We don't care about the base 2. We just need to make these exponents equal. And we can solve that. It's a basic linear equation. Subtract 3, divide by 2, and we get 6. Okay? That's the idea. Well, what if we don't have an exponential? We got the plus 4 in the way. We'll get that 4 out of there first of all. Now I got 3 to the 5x equals 81. Whoa, wait a minute. This is 3 to some power, but this is not. But you know what? I got a feeling that 81, if we take 81, that's 9 times 9, and that's 3 times 3, doing some prime factoring here. 81 is 3 times 3 times 3 times 3. That's 3 to the 4th power. So if we do some prime factorization, we can rewrite this as 3 to the 4th power. And now we know 3 to this power equals 3 to this power. So these two powers must be the same. 5x equals 4. That's an easy equation to solve. Let's divide by 5. And x equals 4/5. See that? So first of all, got to get that power by itself. And then we've got to rewrite this as a power. And hopefully they have the same base. If they do have the same base, then we're home free. We can make the exponents equal. Okay? Whoa, what about this? Well, this is a 5 to a power. This is 1/5 to a power. But it seems like we know something about this. What kind of power would put a 5 on the bottom? Well, a negative power would, right? So let's rewrite this 1/5 as 5 to the negative 1. Now things are looking more similar. We got powers of 5, but let's go a little further. Power to a power, we multiply. So this is 5, and negative 1 times 3x is negative 3x. Now we've written both as the same power. We've got a power of 5 and a power of 5. So if we got the same bases, then these two little green exponents should be the same. Negative 3x must be the same as 6. And we can solve that. Divide by negative 3, and x is negative 2. Okay? So if we've got a fraction, remember that fraction, especially if it's got a 1 on top, can be written as a negative power, and then we have the same base, and we can go from there. Okay. One more. So again, we've got a 2 here. So we'd like to write this as a power of 2. This is 2 over 1, or 2 to the negative 1. This is, multiply those, we got negative 5x. And so the base is the same, so these two powers or exponents should be the same. All right, and divide by negative 5. 16 divided by 5 is 16/5. And since we're divided by negative, it's going to be negative 16/5. All right? That's the idea there. Okay? So if we can make both sides, we can write both sides, that is, as the same base, then the powers must be the same. So one more good application of exponents and exponential functions is computing compound interest. And compound interest is the power of your bank account, all right? So we have this formula here. This is called our compound interest formula. A is the amount we have in the account after our initial investment of P. So P is the initial investment. The interest rate is R, and T is the time, okay? And N is the amount of times compounded per year, all right? If you're not familiar with compound interest, what that means is if I put $1 in the bank, and at the end of the year or at the end of some time period, they give me a 1% interest. Well, now I have $1.01. So 1% of $1 is 1 cent. So I get that 1 cent and my bank account goes up. If I leave it in there, then the next time period, maybe it's the next year, I get another 1%, but it's not 1% of the original, it's 1% of what I have now. And 1% of what I have right now is 0.0101. And if I add that to what I had before, now I got 1.0201. Okay? And if we keep going, now next we'll get interest 1% of this. So compound interest means we don't just get interest on what we started with, we get interest on the interest. So this 1 cent was given to us by the bank because we left our dollar in the bank. And then we got interest on the original dollar and we got interest on that 1 cent. Okay? And then we'll get interest on that interest. And that's what we call compounding interest. We're getting interest on the interest. Interest is money that the bank gives you to let you have their money for a while. All right, so let's say you invest $1,000 in the bank and we have 6% interest a year. All right, so that's our annual interest. We want to know how much money we'll have after 10 years if, let's compound it annually. That means we get interest once a year. So let's enter the numbers into our equation here. We have the amount of money we put at the beginning. And we got 1 plus the interest rate. So rate needs to go in as a decimal. 6% is 0.06 over annually. Annually means once per year. Once per year. So N is 1. N is the number of times we compound each year. And we're going to go for 10 years. So if you enter this whole thing just like this in your calculator, 1,000 parentheses 1 plus 0.06, you obviously don't need to put this divided by 1, to the 10th power, you'll get $1,790.85. You leave that $1,000 in the bank. Now, if we compound quarterly, this means 4 times per year. Then we're going to get a little different amount. So we have 1,000 times 1 plus 0.06 over 4 to the 4 times 10, or the 40th power. All right. We get $1,814.02. So what happened, little history here, banks were saying, all right, we'll give you interest once a year, and we'll give you that interest payment at the end of the year, and here you go. Get $790. Then some banks said, well, you know what? We'll give you a little better deal if you come put your money in our bank. We'll give it to you 4 times a year, but we're not going to give you the full interest. We're only going to give you 1/4 of the interest. All right, so 4 times a year, you get 1/4 of 6%. That's 1.5%. So every few months, they'll give you 1.5%, And then they'll give you the interest on that and then interest on that. But what happens is you're getting interest on interest 4 times a year. So it comes out a little bit higher. Okay. Now if we go monthly, which means 12 times per year. Okay, let's see what our interest comes out to be, or our total amount comes out to be now. So again, another bank said, well, wait, you know what? Instead of giving it to you 4 times a year, we'll give it to you 12 times a year. Now, we're only going to give you 1/12 of your interest, but each month we'll give you a little bit of that interest we owe you. And what happens is it gets more and more and more, right? Okay, so you're getting interest on interest. And let's see what that ends up being. So you get $1,019, or $1,819.40. So first bank said, hey, we'll give you interest once a year. Second bank said, you know what? We'll give it to you 4 times a year. And look, you'll get, what about $24 more just for banking with us? And then the next bank said, well, you know what? We'll give you interest 12 times per year. Every month we'll give you a little bit of interest and you'll get more. Well, it is true that you'll get more, but notice you're not getting that much more with this bank. Okay? Because when it goes from 4 times per year to 12 times per year, it didn't increase quite as much. And then last but not least, what if we compound daily? That's 365 times per year. Okay, so the next bank said, hey, come bank with us. We'll give you a little bit of interest every day. You'll still get 6% interest, but we'll divide that by 365. And every day of the year, you'll get a little bit of interest. And in the end, you'll turn out better. You'll get to make more money. Well, go punch this in your calculator and you'll see. You do earn a little bit more, but it's only about $3, actually a little less than $3 more. So here it went up. Here it went up about $24. Here it went up $5. Here it went up a little less than $3. So the more times per year it is going up, you do end up with a little bit more money, but not that much more. In fact, that leads us to an interesting situation where we can say if we have $1 invested at 100% interest for 1 year. All right, so this 100% interest means they're going to double your money. All right, then we get this formula. We're going to put $1 in the bank. So our initial amount is 1. So we don't really need that number there. And we get 1 plus 100% interest is 1.00, which is 1. So our interest is 1 divided by n, the number of times compound, to the nth power. Okay? So this one's worth cranking out. So let's get our calculator. So here we have our formula in Desmos. We got 1 plus 1 over n to the nth power. And we're going to take that n and we're going to crank it up. Right now, if n is 1 time per year, we double our money. We get 2 as our total amount of money. If we get it, let's see, 4 times per year, if I can get it to land on 4, looks like there's a 1. Well, let's go to, all right, 10 times a year, 2.5. 90 times, so if we compound the interest 90 times, we'll walk away with $2.7. If we compound it 170 times, 2.71. If we move up here to about a year, 365. See, right about there, a little less. Okay, we go, well, 2.7145. And we notice as the number of times compounded moves up, notice it's not changing that much. The numbers, the real small numbers are changing. But if we were to compound it 1,000 times, we'd have 2.716923. Well, that wasn't very different from what we had a little while back here. All right, so we start to see that the numbers start to zero in on a certain amount, all right, on a certain number. And there's a special number that is getting close to, and that's a number we call E. So we say this has a limit. It will never quite reach it, but it has a limit, And that limit is the number about 2.71828. And that's a number called E. It's a very special number. It shows up often. We call E the natural number, or we call it Euler's number, who was named after about 400 years ago or so. All right, so that is the number E. Now let's go ahead and graph it and see how that works. So E is a number. It's about 2.71828. It's just a number, like pi. All right. So we're going to graph e to the x. So that's about 2.718 to the x power. So it's real close to 2 to the x or 3 to the x. So we can just graph that. We know it goes through 0, 1. And when x is 1, y will be about 2.718. All right, so we'll mark our axes here. Got the point 1, comma 2.718. It's going to go up about like that. And we know it's going to go down to the left, getting closer to the horizontal axis, something like that. So this is the graph of y equals e to the x. That's what it would look like. And if we have y equals negative x, remember that's 1 over e to the x, or like 1 over 2.718 to the x. And it's just going to be a reflection. So we're going to go just flip it around the y-axis. We'll go up to the left, down to the right, and that's y equals e to the negative x. So when you see e, just remember it's about 2.7, all right? So it acts very similar here, okay? So now we can come back to our compound interest problem here. Now we can see how we can compound this interest continuously. So we did compounding annually, quarterly, monthly, daily, but now the next bank says, hey, I can do this all the time. So we have the formula A equals P times E to the RT. And this is an important formula to know. And so it turns out that the compound interest formula just simplifies to this. So let's say the bank wants to give us compound interest continuously. So this bank says, we'll give you interest all the time, every moment of every day. So let's take our P, our principal, was $1,000, and we're going to enter it into our equation. So we have A equal $1,000 times E to the rate, which was 6%, 0.06, times T the time. And the time was 10 years, right? So now all we got to do is go to our calculator and plug this in. Now we're going to use Desmos, but you could use your TI-84 just as well, maybe even easier. So on your TI-84 you'll see a button. You'll have a button that looks like this over next to the 4, and it says ln and E. There will be a little e to the x. You can use that, e to the x, okay? So if you're using your TI-84, go find that there on that e to the x, all right? If you're using Desmos, pretty much any calculator will have an e to the x button. You might have to hit a second button like that. If you're using Desmos, you can just type the letter E. Desmos knows that E, and you've got to put this in parentheses up here, 0.06 times 10. And there you go. So we end up with 1,822, and if we round up 12 cents, 1822 and 12 cents. All right, so notice that this gives us 1822 and 12 cents. So the moral of the story is the bank that says, hey, we'll give you interest every moment of every day. This is continuously. Well, the interest isn't that much bigger than 365 days a year. If we got interest once per day, you'd have $1,822.03 after 10 years. If you got interest every millisecond of every day, and that'd be continuously, we get $1,822.12. So 9 cents more than that. So the moral of the story is this: banks now always just use compound continuously. I should say almost always, but that's the key, because it all just That's the best we can do, and that's just the common standard now. So, all right, well, hope that helps, and good luck working with exponentials.